Yeah, so last time we ended with column operations. We didn't state all of them, we just really said they exist. But why don't we go through and describe all the column operations? So column operations, we found, we'll discover that they are type 1, 2, and 3, right? But acting on columns. And they will look like the same matrices we'll find as the row operations, but instead we're going to be multiplying them on the right. So if you know your row operation matrices, then you'll probably be able to do column operations. So let's find, so for the first one, let's find A, B, C, D such that it flip-flops C1 and C2. So those are like columns. So what should A, B, C, D be? So if you know your row swap matrix, you should be able to do this one. So just to get started, if you do the multiplication, is A C1 plus C C2, and then B C1 plus D C2, and you want this to equal C2 C1. So what do A, B, C, D need to be? Lowercase ones. Same thing with row swap, right? There's nothing much different here. So if I have A C1 plus C2 equals C2, what do you know about A and C? Well, if A is equal to 1, then you're left with a C1, right? But I want a C2 in that position. It's the other way around, yeah. So this implies that A would need to equal 0, C would need to equal 1, and then right, the second position says that BC1 plus DC2 equals C1. So you want to get rid of the C2, right? So D is equal to 0, and then you want to leave 1 C1 there. So that's exactly our elementary matrix for row swap. So how is a row swap different than a column swap? Well, on the one hand, row swap is multiplying on the left. On the other hand, column swap is multiplying on the right. So let's just kind of call that. So if I have, let's say I have 0, 1, 1, 0 times x, y, z, w. What does this do? What does this matrix do to the matrix x, y, z, w? Swaps what? So in this case, is it row or column? Rows, yes. So on the other hand, if we multiply that same matrix by the same matrix on the right, what do we get? Right, then I get a column swap. So do you see the difference? So multiplying the same matrix on the left or the right, an elementary matrix, on the left means row swap, and on the right means column swap. So this is a great, example of, why you have to be careful when you flip-flop the order of multiplication. Okay, so let's go back to our, and let's do the same thing, but for type 2s. Suppose you want to multiply a constant times C1, or your column. What would A, B, C, D need to be? Again, we have a, I'm not going to write it again because we have it up here. So look at this line here and determine what A, B, C, D would need to be so that you have alpha C1 and C2. So I have AC1 plus C2 is equal to alpha C1. So what's A? Or alpha, yeah. And then what would be C need to be? Well, so I'm looking at this one, right? C would need to be 0 because I don't want a contribution of C2 in the first position. What would B need to be? That would also need to be 0 because I don't want a contribution of C1. And then what would D need to be? D equals 1. I want to keep that the same. Good. All right, so similarly, let's just see the difference. So if I do alpha 0, 0, 1 times x, y, z, w, what is the result? So multiplying the left, what do you get? So what, let's just say what operation is it? Right, this is the multiply row 1 by alpha, right? So it would be alpha x, alpha y, z, w. But if you do the same thing, but multiply on the left and on the right instead, then you get multiply column 1 by alpha. Okay, questions about that? Everyone see the difference? Why is that? Oh, so last time, oh, it's just hard to see. This was last time. This was the type 2 operation that multiplies row 1 by alpha, right? And if you don't understand, then just do it out for yourself and see that if you do the multiplication, right? The first position is going to be alpha x times 0 z, alpha y plus 0 w, etc. So now in the second one, I'm doing the same matrix, but I'm multiplying on the right instead. So now just do it out. So x times alpha plus y times 0, that's alpha x. X times 0 plus y times 1 is y. Alpha z times alpha plus 0 plus times w is alpha z, right? Did you see the multiplication? Yeah, sure. The first one, the row swap. Yeah, so just do the type 2. So when you do the multiplication, it's alpha times x plus 0 times z. So that's why you get alpha x. Yeah, these are the same matrix, right? However, notice what happens when you do the second position, right? It's alpha times y plus 0 times w. So my second alpha goes here. So like if you know the row swap, if you know the row operation, then you immediately know the column operation. All right, so let's do a type 3. Let's do the same thing. Maybe I'll write this one out. So it's AC1 plus C2, and then it is BC1 plus DC2. And I want this to equal C1, C2 plus alpha C1. All right, so this is a type 3 operation, right? So now remember, instead of rows, I'm doing this in columns. All right, so let's do the same thing. What would A, B, C, D need to be? So how do I get these two things to be equal? So this needs to equal this, and this needs to equal this. Yeah, A equals 1. How about C? So little c. What would that need to be? Yep, 0. Right, your first position is just C1. And then, oh, 1, 1, 0 alpha. Yeah, I agree. Actually, it would be alpha 0 or alpha 1. Right, because yeah, so so the entry here means you're contributing twice or alpha times C1, and then B would need to equal yeah, so that's B is alpha, and then D would need to equal 1 because there's only one C2. Oh, okay. Yeah, so, and notice that was your type 3 operation for a row swap, or for, if you want to say row swap. A type 3 operation for rows. So let's just make sure we remember that. So what is this as a row operation? What is the row operation that is 1 alpha 0 1? So which row is changing? So if it's going to be the first one. Remember that when you do row operations, the row that looks like identity will be the one that's not changing. So the one that has something interesting is going to be the one that is changing. So now this is going to be row 1. And what are we going to do to row 1? We're going to do row 1 plus alpha row 2. And if you do the multiplication out, that's exactly what happens. So it's x plus alpha z. Yeah. So this is this first matrix here, 1 alpha 0 1, is it represents the row operation row 1 plus alpha row 2. So this gives x plus alpha z and y plus alpha w. So this would be zw. So what to understand is that when you do a column operation, so you take this 1 alpha 0 1 and put it on the other side, you expect it to be different, right? Because you can't flip multiplication and expect it to be the same. But the idea is that when you do flip elementary matrices, they're not the same, but they're pretty close. Like in terms of one is a row operation, one's a column operation. So why don't we just do the multiplication now and then say what the column operation would be? So this one is x, right? X times 1 plus 0, y times 0. And then over here is alpha x plus y, right? Alpha times x plus y times 1. And then here is z. And then here is alpha times z plus w. So can someone say what the column operation would be? So which column is changing? The second, yeah. And how is it changing? So for type 3s, right, there's always, the column stays the same, then you're adding something. So what are you adding? Yeah, you're adding alpha C1. Notice that this part here is alpha times the first column. So for type 3s, it's a little bit different, right? For when you multiply on the left, this is looking like you're changing row 1. When we multiply on the right, this looks like it's changing column 2. So it's not, the indices of the rows and columns won't stay the same, but it's still going to be this type 3 operation. All right, we won't really focus too much on column operations because what's very nice is that you don't need them. That row operations are enough. However, like that, they might come in handy when you're doing your row reduction. You know, sometimes we might see that, oh, I can flip these two columns and then calculation might be easier. But this is just to say that if you do happen to do that, notice that you're going to be multiplying an elementary matrix on the right. So don't focus too much on column operations, but row operations are like enough to work with. But there are column operations. Yeah, it's a bit of a culture shock, right? You're so used to row operations, now we're suddenly thinking about columns, but it's not a big deal. I think the takeaway, if you want to, you know, boil this down into one thing, the takeaway multiplication of elementary matrices on the left are row operations. So a big thing is just remember that it's on the left. The same thing on the right are column operations. So again, just remember, if you see a multiplication of an elementary matrix on the right, it's actually doing something to the columns, not the rows. Again, if you just do them out, then you can see them. Okay, so let's talk about inverses again. So something we want to define is that two matrices, so this is n by n, are called row equivalent if you can perform row operations to get from one to the other. So for example, the row echelon forms are equivalent, or are row equivalent. So let's say like this, row echelon forms of the matrix A is row equivalent to A. All right, does that make sense? So basically everything that we were doing in like the first couple sections, we're doing row operations. Now we're saying that, okay, every time we're doing a row operation, we're looking at a different matrix, just with some row operation. And we're going to call all those, every step in that process, every matrix will be called row equivalent. So those, every matrix in your sequence of row operations are row equivalent. Any questions on that? Okay, so let's express this as a in matrix algebra form. So we know that row operations can be expressed as products of elementary matrices. So A is row equivalent to B if what? If there exist elementary matrices that when you multiply on the left to A, you get B. Everyone see how these two statements are the same? Okay. Okay, cool. So here's a statement that we did last time. Matrix A, so this is n by n, is non-singular. Or let's do the other way around. If matrix A is row equivalent to the identity matrix, then matrix A is what? What do you know about matrix A if it's row equivalent to identity? What can you say about matrix A? Yes, it's non-singular. So that's A times E1, E2, En is equal to I. So yeah, non-singular means has an inverse. So by the way, what is the inverse? Yeah, A inverse is all the E's. And you have to keep track with the order, right? If you flip the order, then it may not be the inverse. Okay. Well, here's something interesting. All right, let's do some algebra. Okay, I have En minus 1, E2, E1, A is equal to I. So here's my question. Solve for A. All right, how do you solve for A? So think about that. Like, pretend these were numbers with an X in it. How would you solve for X? Yeah, you would divide, right? So division is kind of weird in matrix world, right? How would you do division? What's the kind of the analog of division in matrix world? Okay, yeah. So that's what it is. Multiply by reciprocal. But what do you mean reciprocal in matrix world? Like what do you mean by reciprocal? Because reciprocal is particularly to numbers, right? But what is the reciprocal in numbers? Like what is that? What is it? So I'm just looking for the magic word. Yes, multiply by the inverse. Yes. So I need to multiply inverses. So I can't just do it randomly, right? Because remember, you can't flip-flop to matrices necessarily. So how could I solve for A? Yeah, how could I do it? How can I, so think that A is trapped by all these E's. So the first step to get rid of these E's, what would you need to multiply by? What inverse would you need to multiply by? So it's inverse of something you multiply by. So what do you think you could do? We don't, let's say we don't know what A inverse is, right? Well, that would be solving for A inverse, right? Um, yeah, so inverse of E, 1 over E um, of, let's say we don't know what that is though. We don't know what is that. So let's do it like one step at a time. What will be the first thing you could multiply by? And there's a lot of E's here, right? So which E should you multiply by? The E, the nth one, right? So notice if you multiply by En inverse on both sides. So remember last time we talked about what the inverse of elementary matrices were, right? It was like the undoing of the row operation. Let's see what you get. You have En inverse, En minus 1, exactly. You have to go backwards. So to undo all these things, you have to undo them in order. Okay, so let's go through and see, let's look at our cancellation. What is En inverse times En? So one, or identity, we call one identity in matrix world, right? So what's left over is En minus 1, E2, E1A. Okay, what's I times E inverse? Or sorry, what's I times En minus 1? Yep, by the nature of the identity matrix, it's the matrix where when you multiply, it doesn't change. And then, so that means that this is En inverse. Okay, what's the second matrix you multiply by? So I'm trying to get to A, so what would, yeah, I would multiply by En minus 1 inverse. Now, big question, where do I multiply En minus 1 inverse? Where do I put it? Do I put it here or do I put it here? So do I put on the left or do I put it on the right? So this step here is multiply En minus 1 inverse on both sides. First of all, does everyone see what we're doing? So the process of what we're doing is doing one step at a time. We're shaving away at these e's until we get to a. So the first thing we did was we got rid of the leftmost e. It's the only way you can get rid of it is multiply by the inverse. And so now we're in the next step, we're getting rid of the next e there. But the question is where do I write my e? Do I write it here? Or do I write it here? Which one? Only one of these is correct. The left one. Yeah, why the left is because, well, what we're doing is, well, this thing is equal to this thing, right? And if I multiply this matrix on the left-hand side by something, then I should multiply this matrix on the left by something. Does that make sense? So it's just like normal algebra, right? Where what you do to one side, you must do the other side. So if I multiply this matrix by e to the n minus 1 on the left, then I must multiply this matrix by e to the n minus 1 inverse on the left. So this is to be careful about with matrix, because you do have to care about where you multiply. Okay, everyone understand that nuance there? Okay, good. Okay, so I'm not going to go through every single n because I don't know how many we are. So let's just explain. Let's say we get down to E1A and someone read out to me what the right-hand side would look like. So the big question is, what E is here? There's some inverse, E inverse, but what would it be? So N is the one out here on the rightmost, right? So that's out here. Yeah, so it's 2 and then E3 inverse, right? So no, it's different, right? When you had, here we multiply, you know, it looks like it's decreasing n minus 1, but when you do the inverse, it's because of how you're multiplying it, the order is reversed. And finally, A equals E1, E2, and then En, En. Okay, everyone see that? Can someone say what this implies? What was our first statement? Is that we had A times a bunch of elementary operations is equal to identity. And here we solved for A. So remember, so this implies A is non-singular. And we did all these steps that were true. And then here, this statement is also true for any non-singular matrix. So what does this mean? So now we can classify all all non-singular matrices. This is saying that all non-singular matrices are some product of row operations, yeah, of elementary matrices. Right, remember the inverse of an elementary matrix is still elementary, right? But like maybe there's negative somewhere, maybe it's 1 over something. So that's what it's saying, is that if you, and that's pretty powerful. So if you have any matrix that's non-singular, so it has an inverse, then it must be able to be written as a product of elementary matrices. So essentially this is saying that all non-singular matrices are just a bunch of these elementary matrices. So that's kind of why they're called elementary. They're kind of the building blocks. So you can think of elementary matrices are the building blocks for all non-singular matrices. So everyone see that? In other words, you can always factor a non-singular matrix into elementary matrices. That's pretty cool. Any questions on that? So you might be asked, here's a matrix A, write it as a product of elementary matrices. We know you can do this, right? Okay, so let's continue. And this is saying that we have two things now about non-singular matrices. Well, a couple, maybe more than two. So the first thing we have, that by definition they're invertible, has an inverse. The second thing we can say is that they're row equivalent to identity. The third thing we can say is the reduced row echelon form is identity. These are the same statement. And the last thing that we just said was that they're factorable into elementary matrices. Okay, so any questions on that? And everyone see why this is true? Okay, so let's make up another fact about non-singular matrices. Okay, let's have a matrix A times X is equal to 0. And this is n by n. Sorry, what if A is n by n, and maybe I should be more explicit. All right, let's say I have A is n by n, and I want to multiply it by a vector x. What dimension must x be? So we'll review. As a vector, it would need to be n by 1, right? Because vectors have the 1. So, and what would the product be, the dimension of the product? N by 1. So let's suppose that you have, we've seen this before, right? This is our matrix equation. Let's say that A times X is equal to the 0 vector, n by 1. Okay, let's think about that. Have we seen this before? What do we know about matrix equations, first of all? Like, what do we know about AX equals B? Do you remember what that, can you rewrite AX equals B as something? Do you remember seeing AX equals B? What could you say about something that says AX equals B? So this is going back to like the first couple sections. It's good to remember. Let's say I have A, B, C, D times X, Y is equal to NN. And then you have AX plus BY, CX plus DY is equal to NN. All right. What can you do from here? If I wanted to solve for XY, what would you need to do? Should be like immediate. Okay, if you don't like the letters, we'll put numbers. How do you solve for XY? Do we know how to solve for XY? Okay, x plus 2y is equal to 5. What else is true? 3x plus 4y is equal to 6. Okay, what is this? Yes, every matrix equation can be represented as a system of linear equations. And while we're here, what's the other thing? How would you go about solving this? Like, what type of matrix do we look at? Do you remember what it was called? So how do you solve this linear system using matrices? You did a lot of homework on this, right? It's an augmented matrix, yeah. What goes where? One, two, five, and 3, 4, 6. Good. Okay, so ring the bell again. Matrix equations like AX equals B are linear systems, are augmented matrices. All right, what about AX equals 0? What type of linear system is that? Pretends those 5 and 6s were zeros. Does that have a, do you remember that special name? It had a special name. If you don't remember the name, do you remember a possible solution for X? Can you find what X could be? Sometimes free variables come into play. So if I, do you know what X is equal to? Yeah, so there could be free variables in there. But what's always a solution to AX equals 0? Zero, yeah. x equals 0 is always a solution to ax equals 0. And yes, if otherwise, there are free variables. Not otherwise, I should say. If there are more solutions, there are free variables. Okay, do you remember what these systems are called? Does the name ring a bell after talking about it? It's homogeneous. Remember when you have an augmented matrix with zeros on the end of it, that's a homogeneous system. All right. So just a little, remember that. So let's say we have a homogeneous system where A is non-singular. What are solutions? What is a solution for X? So if A is non-singular, what does that mean? Let's say that first. Other way around, it has an inverse. How can you solve for X? So again, how would you normally solve for X if you see X equals 0 in real number world? Yeah, why does X equal 0? Yeah, get in the habit of saying A inverse. I know what you mean when you say divided by. Yeah, get in the habit of saying inverse, but good. It is, because it has an inverse, you're able to multiply both sides by A inverse and actually solve, right? That's what this one makes non-singular matrices so nice, is that you can actually do algebra. So that means that's the only solution, because I solved for it. But notice if A is, if maybe say it's say like Bx equals 0 is singular, is that I can't multiply on the left by anything to solve for X. Do you understand why? So Ax equals 0 is an equation. It's okay. Ax equals 0 is an equation. And then to solve for X, what you do is multiply both sides by A inverse. So by doing that, you get an identity. So identity times X is just X. And then the big thing is that anything times 0 is 0. So that's why you get X equals 0 is the only solution. So you can only do that if A has an inverse, right? But if it does not have an inverse, then you can't cancel out. Yeah, so non-singular means you can cancel, but if you have a singular matrix, you can't cancel. So there's no cancellation here. So how would you solve it? In this case, you would do row operations. Right, like we've done in sections, in the first couple sections. So what is very nice about this is that if you know the inverse of a matrix, you can solve any system. So let's give an example. Let's do 1, 2, 3, 4 times xy is equal to, let's just even do 5, 6. Here's a system of equations. The idea is that you can multiply both sides by the inverse of this matrix. So remember, the inverse of this matrix is 1 over 4 minus 6 times 4, 1, -2, -3. So if I multiply both sides by this thing, this whole thing is identity, right? Because that's the inverse. Then I have xy is equal to whatever that is. Was that 8? -15 plus 6, -9. Does that make sense? Everyone understand that? If it has an inverse, it makes solving this very easy, where before we need to do our system of linear equations. Sure, yeah. So I'm doing the matrix multiplication. So this is 20 minus 12 is 8. And this is -15 plus 6 is -9. And then this 1 over -2 thing, this comes from the formula that we derived for inverse of 2 by 2. So again, this whole thing, this thing is your A inverse. Is that better? Great. All right, so do we understand kind of what's so nice about non-singular matrices? Is that we don't have to go through the whole tedious process of doing row reduction. If we know what the inverse is, we just first do it. Okay. But now let's actually, that's all to say that if you know what the inverse is, right? If you don't know what the inverse is, you're in a bit of trouble. Oh yeah, so actually I wanted to say the big takeaway of all this is to say that AX equals B has a unique solution. If A is non-singular. So in particular, the one that's kind of more interesting sometimes is AX equals 0 has only X equals 0 solution. Right, what is the unique solution for AX equals B? It's X equals A inverse B. So that's pretty nice too, right? There's only one solution whenever you have a non-singular matrix in a matrix equation like this. Everyone see that? So non-singular just makes like algebra a lot easier. So let's think about how to find inverses. At the same time, we'll even determine if a matrix is singular or not. Okay, so let's do a little trick, and we're actually going to find the inverse of matrix is actually going to end up being things we've still done in the first couple of sections. So recall that if I have like A times X is equal to I, the identity, this is big X, so it's a matrix. What is X? A inverse. So what I can do, this is essentially saying, so like maybe for like a 2x2, A, B, C, D, and this is actually how we prove the inverse of a matrix, is that we're solving this system. A, B, C, D times X, Y, Z, W is equal to 1, 0, 0, 1. However, that's a little tedious. So what I could do instead is say that, okay, well, what I'm really doing is, now remember like when we were doing augmented matrices, solving the system, doing an augmented matrix is equivalent to solving the system. So solving for X in here is equivalent to solving the augment A augment I. So what do I mean by that is that, so what goes into solving for X here? Like, how would you do that? So first, let's just look at the matrix equation. How do you solve for X here? So think about what we talked about with non-singular matrices. How can you solve for X? So we don't know what A inverse is, but how could you, so let's look back at some of our slides. If I have AX is equal to I, how can you solve for X? How do we get rid of A? Yeah, so if A is factorable into elementary matrices, then what you're essentially doing is at every step, we're doing what we talked about was to multiply by inverses. So how would you go about solving this as well? Notice that when you do one row operation, you get closer to solving for X. So how do you solve this augmented system? Is you do row operations. Right, so for example, if I have A, B, C, D, 1, 0, 0, 1, you want to do row operations. So how do we know when we're done with our row operations? Notice that at every point when we do row operations, like up here, when we're done with row operations, we get A inverse. So whose product is identity. So what we want to do is turn AX equals I into IX is equal to A inverse. So the idea is that when solving this augment, you want to do row operations to turn A augment I into I augment A inverse. Something we talked about last time is that finding the inverse is equivalent to doing row operations. So how do you solve for A inverse? Is you find reduced row echelon form. And at the same time, you are keeping track of the elementary row operations. Okay, so let's just do an example. If let's say, I'll just make up a matrix 1, 1, 2, 0, 1, 1, and 0, 0, 1. So let's do an easy one. So I want to find the inverse of this. So essentially what we're doing is we're saying, okay, we want to find some matrix X that is equal to the identity. Oops. So we're solving for X. So we can make an augment. To make life a little easier. And at every point when we're multiplying by an elementary matrix, we keep track by doing row operations on both matrices. So we know when we're finished is that when we do all these row operations, at the end we'll get I times X is equal to A inverse. Okay, so can someone say, what is your first step into putting the left matrix into reduced row echelon form? It's already nice, right? It's already in row echelon form. So how would you finish it off into reduced row echelon form? What's your first step? So again, we're putting in reduced row echelon form. Yeah, I can do row 2 minus row 3, and I can also do row 1 minus 2 row 3. So row 2 to row 2 minus row 3, and row 3 to row 3 minus 2 row 1. Okay, so let's look at the result. So I have 1, 1, 0. Oh, sorry, this is row. I'm changing row 1 into row 1 minus 2 row 3. 0, 1, 0, 0, 0, 1. And now let's do the same thing on the other hand, on the right hand side. So what is row 1 going to look like on the right? What's row 1 minus 2, row 3? Yes. 1, 0, and negative 2. And then what's the second row? Yep. 0, 1, negative 1, and 0, 0, 1. Everyone see that? So the augmented matrix is the tool to make tracking this a lot easier. Otherwise, we would be doing all of these inverses. Or we would be multiplying all these matrices, but row operations amounts to multiplying by matrices. Okay, now what's the last step you would do to put this into row echelon, reduced row echelon form? And again, it's putting the left matrix into reduced row echelon form. Row 1 minus row 2. Oh, look, the reduced row echelon form is identity. So what does that mean? It means that there's an inverse. So let's give me the first row. Oops. So I do row 1 minus row 2. What's the first row going to be? 1, negative 1, and then you add negative 2 minus negative 1 is plus 1. So what we did, we did row operations on the right side, on the left side, and got I back. We did the same row operations on the right side, and we got some matrix back. And that matrix is the inverse. So again, we go from AX equals I. This is a statement of what the inverse is. Into, we replace this by an augment to make it easier. And then we're doing row operations to make I A inverse. And again, what does this mean in a matrix equation? We're saying that X is equal to A inverse. So what is the inverse? So for 1, 1, 2, 0, 1, 1, 0, 0, 1, the inverse is 1, negative 1, negative 1, 0, 1, negative 1, 0, 0, 1. So I'm gonna get the idea. So going through all these elementary matrices, we kind of streamline the process of finding an inverse by just saying it amounts just doing row operations. Any questions on this? Yeah. Definitely with practice will come into play. It's the big thing. So just you put A on the left hand, I on the right, and then you're doing row operations to turn A into I. And again, the algebra behind that is you're multiplying at every point by these E's. And what you're solving for at the end will be what is ever on the right hand side, which is A inverse. Okay. I guess I can sketch of what we're going to do what we're going to finish with 1.5. It turns out that it's probably kind of clear. Something called we'll call it factorization. So some matrices have a factorization into a lower triangular, which I haven't defined, and an upper triangular. Not sure if I define these. But what is a lower triangular? It means that so what is lower triangular? It's a triangular matrix where you have stuff below the diagonal and zeros above the diagonal. And upper triangular matrix is the same thing, where you have stuff above the diagonal and zeros below the diagonal. So we already actually kind of know this based on what we were talking about, but, and here's the claim. Oh, actually, you tell me, can you think of what row operations are or aren't triangular? So let's just do like 2 by 2s. Is this triangular in any way? No, right? Yeah. For it to be lower, there need to be all zeros in the upper right part. And to be upper triangular, there need all zeros in the lower left part. But there are ones there. So neither upper nor lower. How about a type 2? Is this upper or lower triangular? Well, the stuff can be 0, right? The stuff that still could be 0. This is actually both upper and lower. So we call these a diagonal matrix. But how about type 3? Type 3 is the interesting one. Which is this upper? Which is the first one, upper or lower? So lower means the zeros are on the top and the interesting stuff is on the bottom. So since I have interesting stuff on the top, if this one's upper and this one is lower. All right, so pretty much out of time, but I'll give you this thing to think about. If upper is interesting stuff in the upper right, upright, yeah. So if A is non-singular and it has factorization without row swaps, then A can be factored into a lower triangular matrix times an upper triangular matrix. Actually, if I do it this way, it might actually look easier. In particular, these are the row echelon steps. And these are the reduced row echelon steps. All right, so we're out of time, but think about, you know, what operations you would do to get to row echelon and what operations you would get to reduce row echelon form. And then think of them as a sequence, and you can actually figure this out yourself. But I'll do this next time. But okay, I'll see you Monday. Have a good night. And I'll stop recording.